Thanks for coming. And first of all, introduce myself. I'm an assistant professor and Amii fellow with the ECE department and the University of Alberta. So my research focus on the trustworthy AI and particular machine learning, computer vision for structured and unstructured data analysis. So today I will present one of my research themes about anomaly detection. So right now with the foundation models, we know that actually people talk about the data quality more and more. They said that with more data quality, usually with the better quality, the performance will be good. But most of the cases, the data quality is always said that high quality data set is constructed by manual selection and people's feedback. And in today, I will talk about our efforts towards the data curation, and particularly we will focus on anomaly detection. And here we emphasize its vision anomaly detection is because that given the presentation scenarios as what we are right now, the vision gives us an intuitive sense. We can see what is anomaly. We can see what's going on. So in this presentation, though we focus on the vision anomaly, but I want to emphasize that all the insight principles and we design here can be easily applicable to numerical anomaly detection, even the log anomaly detection, and language anomaly detection. So let's start our journey. Hopefully it works. No, it doesn't work. Haha. Oops. So it doesn't work. Okay, it works. My bad. Okay. The process is slow. Okay. So let's talk about what is anomaly. Usually we say that anomaly is something different from the normal case. So usually we say normal is the majority of the case which share a similar patterns. I give an example. I have a daughter. So my daughter is a very active girl. When we were at home, she's active. I can hear the noise. I say, okay, this is normal because the girl is in the house and she is making noise. And one day I noticed that, okay, the girl is very, very quiet. And then I know, okay, something wrong. It's abnormal. So which means that for normal or normality, we usually consider the general case. They share the majority of characteristics, though we may not know how to describe explicitly what is normal. But for abnormal, our human have the sense about, okay, it is different. So we will tell the difference. But for machine learning, for most of the machine learning algorithms, it does not have these properties or capabilities. And anomaly detection is leverage the models have such capability to identify what is strange, what is different from a majority of the cases. And given the specific mathematical formulas or definition, we say that anomaly detection actually is a binary classifications, normal or abnormal. But different from traditional machine learning or classification, we say that we have positive sample, we have negative sample, but here for anomaly detection, we only have the normal sample usually because we say normal corresponds to a major majority. For abnormal case, instead, it does not well defined. So it means that there are some abnormal case easily collect, but it does not cover the whole spectrum of the abnormal case. And therefore, we say that in addition to the binary for abnormal case, we would like to know what characteristic or what features to represent this abnormal. So we call it abnormal localizations. And usually we say that because the normal case is very easy to collect compared to the abnormal case. So from data efficiency, the scenario or setting of the problem goes into we have a lot of normal case. We probably fewer abnormal case or a little normal case or even no abnormal case. From the learning difficulties, it has the same philosophy. For example, here I show several medical image analysis case. So for the grayscale images, we can say that it's a retinal OCT images. The normal is quite similar, but you can see the abnormal cases. They share different morphology and structures. And also for cancer diagnosis, it's a typical examples. For normal case, it's just we use one images to represent because most of the normal case share very similar characteristic. But for the abnormal case, you can see there are heterogeneity in morphology as well as the tumor size. So which means that they differ and they spread out in the spectrum of abnormalities. And thus, given these difficult challenges, we say that learning the normal patterns, which usually share a lot of commons, is relatively easy because we can collect a lot of normal data. But directly learning the unknown prior or abnormality, it's relatively difficult because for one thing, the diversity is too large for learn. Second, we cannot or it's expensive to collect the abnormal cases. And therefore, we will focus on the unsupervised scenario, which means that majorly we will focus on the normal case. And here are several examples of their visual anomaly detection. So as I said, we focus on vision in these talks because it's more straightforward for us to see what is abnormal. And for example, the direct application is about industry inspection and medical diagnosis or even video surveillance or the quality insurance. So all this, if we can use the sensing devices, we call it vision anomaly. And you can see, for example, for the industry inspection, the abnormal is very subtle. It's not like an outlier detection, so the syntax is totally different. They still share a lot of similarity. The semantic is the same, but at the same time, there is subtle local difference. And the anomaly detection or anomaly localization is try to localize such difference. And this is the typical example. We say that, okay, different from the binary classifications, usually we require positive and negative samples to get compared to calculate the boundaries. But for abnormal case, usually we only have normal case. Then what is the strategy to design the algorithm? So the key principle here is that we try to find the black box. Here I use the neural network as a black box to demonstrate the model. And given this black box, we would like the normal data going through this box, and then it's projected even to an even compact space. And it's capsulated by well-defined boundaries by this black box. And all abnormal case or unknown abnormal will project outside of this boundary and even spread out. And by this design, we can enlarge the difference response of the normal and abnormal. And instead of saying that we have a boundary, we usually give abnormal scores. And this score could give us information how abnormality it is, looks different from normal, because sometimes the normal is big, the abnormal is big difference between the normal. Sometimes it's just a subtle difference. So the anomaly score would give us some information of how abnormality the information it is, or we say how close the abnormal samples localized in the out sample space that close to the boundary. So this is the principles. And given these principles, let's first talk about traditional one-class modeling. So for the one-class modeling, you can see here, it says that given different data problems, we try to build a model for each of the samples. So we call it one class. It means that if we train the model 1 on the chestnut, it does not applicable to the, for example, the third CPB board. So that is to say we need to train the model for each of the categories. And this is a long-standing problems. And usually in literature, we somehow summarize them into 5 different categories or paradigms. For example, for the one-class clustering, we just try to find the model into a encapsulate concept space. For the normalization flow models, it's more like we learn its distribution of the normal. And hopefully when we project the abnormal cases, it's directly outside of the inject bounding box. And for their memory, it's more like I try to memorize what's going on for the normal case and for abnormal case. Okay, it's not in my memory. I cannot find the match items to the abnormal, so it is not a case. And for the reconstruction model, which is E here, it's the very classical paradigm for using deep learning. It says, okay, we have a generator. This generator learns to reconstruct the normal case because it does not learn the abnormal case. It won't, or it is incapable of reconstruct the abnormal case. But we will see that just compare the image level pixel difference, it's kind of ear defined sometimes for the local small abnormal. And therefore, recently, a lot of work focus on the knowledge distillation based anomaly detection. Is that given a teacher which represents the blue one, and we have a student, and then the student try to mimic the behavior of the teachers. So, but the student only learn the response of the teacher given the normal case. So it's more like I teach my daughter addition and subtraction within 10. So 1 digit addition and subtraction. I told my daughter 1 plus 1 equals 2, and my daughter is the student, repeated 1 plus 1 equals to 2. Okay, so after a lot of examples, we expect the model know that 1 plus 1 equals to 2. And when we have a query data comes, it says, okay, what is 1 plus 3? My daughter said, okay, I know it because I learned it. The teacher told me it's 4. Good. And what if the common questions is 1 plus 100? My daughter said, I don't know. My mom don't teach me how to add the 3 digits additions. I don't know. Then we know that, okay, the question is beyond what I teach my daughter. It's anomaly. It's outlier because it requires 3-digit additions. So this is the idea of teacher-student knowledge distillation method for the knowledge for the anomaly detection. But we found that sometimes even the student, if the student is smart, it learns much more than the teacher expected. For example, my daughter is very, very smart. I teach 1 plus 1. She can calculate 11 plus 1. He knows that it's just 1. And therefore, we say that how can we guarantee that my teaching only constrain my students' capability within a certain range? So you will consider traditional deep learning require the model to learn generalizability. So it should generalize well. But for anomaly detection, it's a trade-off. The model should generalize well to the normal case, but at the same time, it should be, okay, thank you. At the same time, it should be constrained only on normal data generalization rather than useless for the abnormality. So we design this reverse distillation in B. So instead of directly learn the data flow the same, we say that we design the logic flow as highlighted by the blue one, the green one, saying that I teach my daughter still the addition and subtraction. But instead, we ask the teacher or the student to repeat the teacher's response. For example, I told my daughter 1 plus 1 equals to 2. The student, instead of saying that 1 plus 1 equals to 2, I asked the student to repeat 1 plus what equals 2. So the teacher should fill in the 1 inside and to satisfy this equation. So by this reverse logic, we can further enforce the student's capability on this particular method. And we say that this is the design of the blue one we call the bottleneck layer and reverse recover of the features of the teachers. Enlarge the discrepancy response between normal and abnormal. And regarding the design, so this is the general architectures, but I don't want to go to the detail. We just look at the right figures. So you can see that we highlighted abnormal areas or normal areas using the red bounding box or box and the yellow or the blue box. So you can see that during the process, the teacher represents the abnormal case by blue. And the student try to interpolate from this logic, we call it bottleneck layer, to extract information, recover the information of the original information, but because the student only learn how to recover the normal case from this compact logic, and therefore it does not able to reconstruct the abnormal case, and therefore for the anonymous regions we can see the representation between teacher and student get a very large degree. But for the similar normal regions, it's very close. So by compare finally the agents between them, we can identify what is abnormal. And here is some visual examples. And compared to the state of art, we can see the localization performance is very good because we compare the reconstruction differences. And also, we say that the method is generic. It's not only for vision signals. It can also apply to numerical signals or different domain. We didn't fine-tune the model. We trained the model on the different set of medical images and compare all the previous methods. We still, the last line is the reverse distillation. It still gets very, very good performance on localizations. But still, we say that sometimes, especially for medical, in addition to the normal case, actually we have collected some abnormal case. Not too much, but we have some. How can we use this one? The method actually can easily extend it to such scenario. We can just modify the loss functions, saying that, okay, if we have abnormal case, we want the students fail to reconstruct a representation of the teachers. At the same time, because we say that we only have several cases of abnormality, so we just reweight the mechanism in the loss functions. And we try this easy extension to the very challenging task in medical. It's called whole slice imaging anomaly detection. So we can see that only 5 abnormal patches, we can boost the performance. And with only 2% of the performance, 2% of the abnormal case together with a lot of normal case, we can roughly get a full supervised training performance. So it means that if we know well of what is normal, we can infer what is abnormal. And I think this is quite natural for humans. But right now, the machine learning does not have such capability. And we would like the machine learning method or machine learning or AI to possess, to have this capability. So we say that we introduce a lot of one-class modeling. We say that for each data, we construct the data to improve the performance. The performance is super real. It's 99% for a lot of cases. And what is the next? We notice that actually if we have different categories, sometimes it's so hard because we need to train the model from scratch. Then we say that, can we have a model have a good scalability so that we train one model on multiple categories? One model can process a set of categories. And to target these goals, we first evaluate the performance. And on the right figure, for example, on the middle RD, so the light pink triangle, hopefully we can see it, corresponds to the performance of the single class reverse distillation performance. It's almost 99% in the benchmark. But once we apply 2 categories, only 2 categories together to train the model exactly the same way, you will notice that the performance is dropped to the light pink star, which is 4 or 5% performance drop. So we would like to know what's going on. Why even we add only 1 categories decrease the performance? So we analyze the problem and we conclude that the drop coming from the cross-class interference. So on the left, we use the blue and the green to represent the different color of categories. So traditional, as we said, that we try to find a very compact representation of the normal for category 1 and category 2. But we feed them into the one model, you will see the yellow regions, which is overgeneralized regions. So it will cover some abnormal case because the model needs to encapsulate normal case from 2 categories. So that is where the performance degrade causes. And how to address this interference? We say that if we know the category information, we just input the category information as their condition. It's straightforward, right? We can train it. But what if sometimes for a lot of automation pipeline, we don't know what is the input because it requires human to identify what it is. So can we achieve the multiple category anomaly detection without exactly know the categories? So here we leverage the vision signals as an insight, as a heuristic motivation. So given the two images, I think just above the multi-class anomaly learning, the titles. So we say that here is two different products. And if we just sample quite grid level, the pixel level information, for example, both of them can extract the grid colors for a particular pixel. Actually, it's very hard to identify which categories the sample come from. But we notice that there is structure difference. The structure difference in terms that it's more about a pixel around its center structure information. So if we consider this structure information by comparing the center pixel and its surrounding areas, the relationship and the similarity scores would help us to identify the category information, though it's not implicit or explicitly, but it does help us know that it's from different category if the structure information is different. So by leverage this structure informations on knowledge distillation, we say that in addition to the pixel level comparison, we also compare the structure information and the inter-structure information. We can realize this multiple. I think we don't want to talk about detail. The key part is that leverage the internal signal structures would help us to combat the challenges by the multiple category overgeneralization limitations. And we test a lot of data set, and we will see that the performance is still good even though it's multiple instances. So we try our best to extend a single class into the multiple category case. It's improved the scalability, but still, what if we have a new category? It means that right now, the concept of category a model can process is limited by how we train the model. And our question is, what if, or can we find one fit all models? So it means that we have the model, we can directly apply it. We don't need to consider, okay, what if there comes a new categories? So this is the real scalability solutions for different anomaly detection. And then here is our thoughts. So first, we have three parts. The first part, A, corresponds to data. So we say that even though we don't have a lot of training data, but even if we are given a set of testing data, usually they contain some abnormal case and a normal case. The normal case, though we don't know exactly which one is normal case, they also give us some reference because we say the normal case usually shares some common patterns. And even for abnormal case, because abnormal case usually also contain some normal regions. So they still can help us to do the reference by comparing the data. So this is one strategy is to find the information of abnormalities among data. So it's more about data mining. The second part is called the vision language model. We know that, okay, right now the resource is there. We train a lot of foundation models. And foundation model train from millions of data, so it have a lot of information, include what is good, is bad, generally. And how can we use this good and bad concept already learned in the foundation model help us to identify the normal or abnormal? So the second step is we can leverage the VLM models. And the third step, C, is about how to combine them. And is there any pitfalls we need to adjust during combine this stuff? So we will talk one by one. We first from the vision language models. So 1.5 years ago, we leveraged the CLIP models. So we know that CLIP was trained on a pair of image encoder and text encoder to match the correspondence between them. And thus, we think if the text and vision encoder align together, can we design the prompting so that the prompting reflects the normal prompting and abnormal prompting. It's more about contrastive. And given this contrast, given the Curie images, we just need to compare the similarity between the prompt and the images. And then we can get a score for abnormality. It looks good because in the text, we also have the domain-aware state. The industry is the domain. It's tuned the models to learn to represent the features in that domain. And the normal, abnormal corresponds to the contrastive pairs. And the class is when we apply it. We know, for example, in the production line, right now, this time it's the CPP board. We just write it CPP board. So it works perfectly for the using the clip. But we found that two methods, and we will show that directly used clip have a very, very poor performance. And we saw that there's two reasons. First, clip was trained on the semantic information. So clip trained on it is dog, it is cat. But it does not say this is a cat with one eye blind. It won't say this. It's just a dog. So it means that clip usually focus on the global information rather than the detail. But usually we say it's for anomaly detection. The sample coming from the same categories. They are dog, they are chestnut, they are CPP board. It won't tell you where its abnormality is, and it cannot detect abnormality. So we need to leverage the clip to describe the fine-grained abnormal details. The second one is domain gap. Though we designed the text prompt using domain information, but image encoder does know that. It's just represent images using the general standard profiles. And how can we do this? First, we use the VV attention, which is a training free, because we said we want a one-fit-all model. We don't want training. So for this VV attention, we just open the black box of the transformers and say that because when we calculate attention, the deeper layer usually consider the global informations, and therefore the vision tokens or the token representation usually not only focus on the local. So we use the VV attention, which use the very early layer of vision encoder, the vision tokens, as their values and propagate or keep track of the local description. And this helps us to define the fine-grained method. The second is about a domain gap. We say that for text encoder, we already have the domain information, but not the encoder, the images. This year, there is a buzzwords about the test time scaling. It means that if we can leverage more computation resources during the test time, the performance boost. And here is our efforts in early days. So we say that we can design somehow a very lightweight adapter by test time adaptation, test time calculations. We can tune the representation of the local features to fit the, for example, here, this is case the industry inspection. And then we tune the features so that it's more fit to the industry inspection scenarios. And by this test time adaptation, we can see the performance. I just want you to focus on the upper left figures. So you can see from the bottom to the top, the clip, which referenced as 34, the performance of the anomaly localization. You can see that because of the two limitations, the performance is so poor, it cannot use. But with the VV attention and as well as the test time adaptation, the performance is boosted a lot. It can be really used in industry already. And we talk about the lower part of the whole solutions, which is vision language model. And then let's talk about the upper section, which is using the data itself. We say for a lot of data, they share a lot of common stuff. We just want to use the freezing image encoder in the clips to extract all this commonality and use, for example, clustering method or nearest neighbor methods to cluster them. If the samples outside these clusters, it is just abnormal. So it is a traditional data analysis algorithm for anomaly detection. And then we say that we will leverage the domain adaptation or test time adaptation to fine-tune the model, to boost the potential of the model. So which is the middle part highlight with the fire. So it means that that is the only part we need to we need to optimize during the inference. So that is the case exactly about the test time scaling. It boosts the performance. So by combining the three cases together, you can see the text encoder gives some predetermined prompts. This prompt is a baseline. Even though we only have one images, even though maybe all the query images are abnormal case, this text encoder giving, for example, a damaged plates, imperfect plates, or a photo of the plates with flaws, all these informations build a baseline saying that if the VLM models is good enough to understand, it will get some reasonable response on the abnormal case. But this is abnormal. This is just the baseline. By using leverage the data characteristic, data similarity, as well as the test time scaling computations, we can further improve the performance. And here is the general performance. So full shot corresponds to we use all the training data to train the model, get the performance on the benchmark. And zero shot corresponds to one-fit-all models without any training. When we use the models, we can apply the test time and so on and so forth, different techniques. So you can see our method only leverage two image or two data to get a comparison. And we get very, very similar performance, just three-point performance gap. But we don't need any training, and the model fit every input image type. So this is about our effort on the zero shot and one-fit-all models. So generally, current status it's very promising, but there is still performance gap. But one key thing is that you may notice that we say that text models give us a baseline, but this baseline it totally depends on the prompting design. But for prompting design, it's biased sometimes. And therefore, how to make this change is our next effort. So we saw that if we have VRM models, right now more and more VRM models and Q&A models comes, they understand the concept or abstract concept of normal and abnormal. We would like to use this very strict but very abstract concept of normal and abnormal embedded in the VM models, which is already there. So we can use the in contextual learning, or with some examples to promote the method to get this performance. So that is to say, sometimes we want to get rid of the textual prompting bias and just show the examples. Given the examples, there is a quite similar with the SAM foundation models. Given the model, it has anomaly detection capability, but it's just general. Given the examples, several examples, the model can directly align its performance on the particular domain and detect the performance. So this is ultimate goal of scaling up the anomaly detection method to automatically identify what is normal, what is abnormal. So I think the time is there. I just sum up. So we say that generally our work focuses on anomaly detection for data monitoring. For this data monitoring, traditional it's one class anomaly detection if we have enough normal data. The performance generally it's very, very good right now. And we want to scale it up. So we try multi-class anomaly detection, but it's still not scalable enough because we say that there are unlimited categories. We cannot compress them or combine them together. So we turn to the help with zero shot or VLM models. I think we will along this path and try to find a real good one without introduced by human intervention of the text prompting, just by data. So if the data tell the story, we don't need human intervention. This is our ultimate goal. And I will stop here today. And thank you. So I'm not sure if there are any questions. Hopefully I explain everything well. But okay, here is a challenger.
Hi, Dr. Lee. Thank you for your insightful talk on advancing the virtual anomaly detections. I'm just curious about the rules of data quantity in this new multi-class or the zero-shot paradigm. Like specifically, how does increasing the amount of data, let's say particularly from the diverse source, like failed collected data, affect the performance of these models? Like, is there a point where additional data yields a diminishing returns, or does actually we give more data won't help and in fact drop the model's performance? So that's my first question.
Okay. So to answer your questions, I think we will depart into the two different cases. So the first case says that the common signals also within that category. So it's called in category data, but it won't improve. So sometimes we say the normal data, for example, normal data share the normal case. So that is to say there is a compact boundaries of the normal data. If we already can learn the normal patterns, so even the more normal data comes, it won't help because there is no more information or knowledge. But generally, for this case, we may bias to overfit on the normal data because we say that different from traditional machine learning. Usually, machine learning is we like the model to generate well. But for anomaly detection, we say that if we only have normal data, we want the model to fit on the normal data at the same time, it should not overfit. Otherwise, there is lost the capability to detect abnormal case. So there is a balance. If there's too many normal data, but they share the very similar normal informations, actually, they might easily overfit. So will decrease the performance.
Right.
The second scenario is the multiple category, as you mentioned. So for multiple scenario, it depends on how similar or how different the multi-categories. If they are very close, then we need to design algorithm very carefully to avoid the over-generous regions. But if the category is different, so it's much easier relatively because there is a big gap in the middle. It's further help us to improve or decrease the performance. So it totally depends on how similar the multi-category it is. So am I answer your questions?
Yeah. Can I ask a follow-up question?
Yeah.
Do you think if we have, let's say, a large amount of normal data and then we do have certain amount of abnormal, do you think we should actually train the model use all of our normal data, or do you think we should right to the point that it's good enough, then we utilize the rest of the abnormal data to train the model?
Okay. Actually, this is a very good question, and we also think about during the research.
Yeah.
So, I just say our discovery. Our finding is that generally using the abnormal case helps, but it's not directly follow the classical training paradigm, saying that the supervised learning.
Yeah.
Because we say that abnormal can be spread vast.
Right.
The several abnormal cases, only the several points. If we directly train using the traditional machine learning method as a supervised learning, it will overfit again to the abnormal case. But their help, if, for example, when we training, we say that we would like the training focus on learn the normal. But because we say that even for the normal, we want them encapsulated within the very compact boundaries. And those abnormal cases actually can help us define the boundary where it is. So wisely use them in the training, but not directly follow the traditional supervised learning could help improve the performance. As we show quickly in the medical image analysis case, only 5 slices of normal with 1,000 normal cases.
Yeah.
We can boost the performance a lot. With 2%, we can achieve the fully supervised learning performance. So wisely use them helps a lot.
Okay. Thanks.
Okay, thank you. Oh, I see the second challenger. Okay.
Hello, thank you so much for the amazing talk. I'm curious to know how these visual anomaly detections can handle cases where we want to capture different types of anomalies, but in one specific domain of data. Because like in different multi-class anomaly detection samples that you showed, I see that domain of data is different. Like one is wood, one is PCB.
Yeah.
In cases of just like processing PCB images, but aiming at finding different types of anomalies that might happen, how can those fit in
the video? Okay.
Yeah.
It's very interesting questions, and it's very challenging. honestly. So I think if it is within one category but with different anomalies, so generally VM models can tell us it's abnormal, but it may not directly tell us where it's abnormal, and therefore there's no means for them to say, okay, what type of abnormal it is. But it usually can also help us to localize. So by its locations, probably it's one information source. Another one for anomaly detection I didn't mention in this presentation is that in anomaly detection, we say that actually it's a ill-defined problem because we only have what is normal, but we want to know what is abnormal. So there are some relationship between these two, normal and abnormal, but they're not identical. So given your case, even we know what is normal, we don't know what is abnormal. It's ill-defined. And therefore, for VRM models, if we know the prior knowledge, similar to other machine learning case, if we know some prior knowledge, use those prior knowledge in design your algorithms, to design your black box, so it can enlarge the discrepancy. It helps. For example, as you said, if we know there are some different category of abnormals, so design it directly in the system design. For example, if we want to VRM models, the strict method is use the prompting to describe the categories you are interested in. I think that helps a lot. But for the other method, it totally depends on the data natures and data characteristics. Am I answer your question?
Interesting. Thanks. Yeah.
Okay, thank you. So, okay, we have more. Okay.
Sorry, Dr. Lee. I just want to ask a follow-up question.
Yeah.
Since there are more and more different kind of data set inside the public domain, let's say we could get the point labels, we could get the segmentation maps, and we could have the text label. So I'm wondering, when you are utilizing those multiple kind of data source, does those data set qualities matters, and how do we control the quality of those data sets to make sure those data actually contribute to the models rather than harm the model performance? So if I can give a quick example, for example, let's say we have some rough map rather than a precise map, would those data set actually being a helpful data point to our trainings, or do you think than actually doing the opposite job?
So you are constrained your question in anomaly detection scenario or the general scenario?
In abnormal detection scenario.
In abnormal detection scenario, I think more data usually helps generally, even though they are not that high quality. But of course, first we would like high quality data.
Right.
But if there is some errors, I think if it's small portion should be good enough, because we said that generally anomaly detection, we would like to amplify the difference between normal and abnormal. It's still in statistics sense.
Yeah.
So it means that if one or two or several errors, and we can, for example, we are lucky we happen to have the quite similar normal cases to contradict to each other, it still helps the model to learn the statistics.
Okay.
But if the model is, if the training data quality is so bad that 100% we know the label is not correct, then we just get nothing. So it's still about data quality.
Right.
So the anomaly detection is a bit different. It's because it's focused on data.
Yeah.
And after the anomaly detection, we can get rid of the abnormal data and train the model with a better performance in the traditional machine learning way. So it's kind of loop back for the whole AI systems.
Okay. Sorry, last question.
Okay, sure.
Hopefully not taking too long
It's
time.
fine.
So I just wondering, what's your opinion on the utilizing data augmentation method in the abnormal detections, or let's step one more step. Let's say we utilizing synthetic data or generative AI to generate some fake data out of the original data distributions. Let's say we use GANs, diffusion models. What's your opinion on those methods?
Okay, actually, that is one paradigm I didn't show for the classical method. There are a lot of methods try to synthesize the data as abnormal, so that we can use this abnormal synthesis data in the normal case as their supervised learning methods. So we also investigate this and published a paper last year. So our conclusion is that if we only rely on synthesis data, because usually synthesis data usually rely on some prior knowledge as the abnormal case. So if the abnormal case, our prior knowledge is complete, it's fine. It's simplifying the scenario. But for most of the case, it is not, because we say that the reason we define it as abnormal because we don't know exactly what is the distribution it is. So generally, if we want to leverage the synthesis data, we say that we leverage somehow in the trade-off between generalization and overfitting. We want some typical case to help us refine the boundaries. But at the same time, we don't want to fully rely on the synthesis data to get the detection performance. So it's a trade-off.
Yeah, thanks.
Thank you. I think the time is up, and I welcome everyone to further follow up in discussion after I step out this stage. And thank you very much. Thank you.